Dear students, welcome back to my YouTube channel. I'm Schmidt and this is an online chemistry tutorial. You get my previous videos from my personal homepage or from your channel. And we were discussing about the topic molecular rearrangement and transformation. And today I'm going to discuss with you a very important molecular rearrangement reactions like Hofmann, Curtius, and Schmidt and Lossen. And we already discussed in previous video the molecular rearrangement that occurs to electron deficient carbonate. And in this lecture, I would like to discuss with you the rearrangement, molecular rearrangement that happen to electron deficient nitrogen atom. Not carbon, this nitrogen. And Hofmann, Curtius, and Lossen, Schmidt, all these four rearrangements are closely related, in which what happens is in every cases carbon migrates from the carbon to the nitrogen. So this is schematically I can give an outline of three rearrangement like this. This is an RCO or RC double bond NH. And in this reaction, a skeletal rearrangement that usually happens in all four reactions are like this. So O minus, it restores and its pi bond, and what happens is this R bond migrate. That means carbon migrate to the electron deficient nitrogen and halogen leave, and it forms a isocyanate. This is the structure of isocyanate. So what happens is R migrate to the nitrogen, it is here, and double bond, it is retained, and there will be a pi double bond, CO pi double bond, right? Isocyanate. R can be alkyl or aryl group. And in all four reactions, only the difference is the halogen, and each case halogen is different. For example, if X is, that is this one is bromine, it is called Hofmann rearrangement, and X is nitrogen N triple bond N, it is called Curtius and Schmidt. And if X is an ester or COR, it is called Lossen rearrangement. So it is schematically I can give outline of all four reagents are like this, and we will get more details in subsequent slides. And only the difference is X is different in each case. So first we will come to the Hofmann rearrangement. It is named after August Wilhelm von Hofmann, and in this Hofmann rearrangement, amide react with this sodium hypobromate or bromine in alkali. It forms first N-bromoamide, and this N-bromoamide, this is shown here. So amide with the sodium hypobromate or bromine in alkali, this is the amide. We are starting with amide, and it forms N-bromamide, and this one react with alkali to form acyl nitrene. This is acyl nitrene and intermediate, and which rearrange to give finally, intermediate isocyanate. This isocyanate convert into amide. So let's see the mechanism in detail. First, we are starting with amide. Amide in the presence of sodium hydroxide, that is alkali, and in the presence of base, it can abstract this hydrogen, and it form this form NH minus, and this can be shown like this also, double bond, or it is like an enolization. It becomes double bonded, it becomes single bonded CO minus. Then this react with bromine like this. This O minus, it restore and it form pi bond. It is here, and it become this pi bond break, and this N nitrogen react with the bromine after leaving one of Br minus. So this nitrogen form bond with bromine, and this bromine will leave. Like one bromine can act as a electrifier here. Okay, then N-bromamide you get. This is N-bromamide. Okay, and in the presence of base, you have a base in the system. It again abstract this H, and it form N minus, and this N minus can form a double bond, like in previous case, like this. It form double bond and CO minus, and this is the product. Then it restore this oxygen pi bond like this, and double bond break, and bromine will leave. Exactly, this bromine leave, and it form acyl nitrate. This is called acyl nitrate. So this CO pi bond will form pi bond, and this double bond break, and there will be a two electrons. This nitrogen get these 2 electrons, and this is acyl nitrate, and it undergo a skeletal rearrangement like this, and this lone pair form a double bond, and if this alkyl group undergo a rearrangement, it goes to the nitrogen atom. So what happens is, this lone pair is used to make up a pi bond, and this alkyl group, this R minus, it goes to this nitrogen. That is, R goes to the nitrogen, and double bond, this become double bond, and CO. This is called isocyanate. Finally, this isocyanate hydrolyzed to give carbonic acid. This is carbonic acid. I will discuss the mechanism in later slide. And finally, in the presence of base, it becomes CO minus, because it abstract, base can abstract this H plus. Then it can leave, the carbon dioxide can leave from this decarboxylation take place from here, and it form amine. So you get amine. So in Hofmann reaction, you are starting with amide, and you end up with amine. Only the difference is this CO minus, even though mechanism is a little bit complicated, the CO minus carbonyl get evolved from here, decarbonylation. So CO group removed from here and are directly attached to this amine. So it forms primary amine with less one carbon atom. That is Hofmann reaction. Okay, Hofmann reaction is usually happens in unsubstituted amine treated with the sodium hypobromate. It gives primary amine with one carbon fewer than starting material. And actual product is actually isocyanate. It is seldom isolated, and it is hydrolyzed. It cannot be stable for hydrolysis, so it gets hydrolyzes at a different reaction condition. If you are using this alcohol in hydrolysis, you get carbamate. This is carbamate. If you are using water, you get amine. And if you are using amine for hydrolysis, you get a urea derivative. So this reaction is also called Hofmann degradation reaction, and because there is one carbon less in the product, and should not be confused with the Hofmann elimination. Okay, so example for Hofmann elimination, and it provides route for making aliphatic and aromatic primary amines. For example, beta-alanine can be prepared from succinamide. So it's an amide. You are starting with an amide. In the presence of base, it cleave here, and in the presence of bromine and alkali, that is Hofmann, and you get this carbonyl get evolved from here, and this carbon directly attached to this NH2, it forms beta-alanine. So example second one, you can prepare anthranoic acid from phthalimide. This is phthalimide. This is a cyclic amide in the presence of bromine and alkali, and you get one of the first it break this one, and it become RCONH2 and CO2 minus. Then this amide decarbonylates, and the carbonyl group evolved, and directly this carbon attached to the nitrogen and it form anthranilic acid. Third example, you can use this for the preparation of beta-aminopyridine from nicotinamide. This is nicotinamide, very famous molecule. The presence of bromine and alkali, and this group get evolved from here, and it directly attached to the amine. Next rearrangement is Curtius rearrangement, and it is named after Theodore Curtius. And in this reaction, the difference is you are starting with acyl azide, RCON3. So we were started with N-bromoamide in case of Hofmann. So in Curtius we are starting with acyl azide, and this azide is prepared usually by treating acyl chloride. This is acyl chloride, right? And with its sodium azide, okay? And you get acyl azide. So in Curtius our starting material is acyl azide. This is the both way we can represent the azide. RCO and double bond and both plus here minus here, or RCO N, it is minus, you have to show, and this is the N2 here, the triple bonded. So this can leave this azide and it form nitrine very easily. So here the leaving group is in Curtius is N2, and it form acyl nitrine. And nitrine has only 6 electrons. It undergo a rearrangement. This nitrogen is electron deficient. This R can migrate to this nitrogen, and this lone pair can form a double bond here, and it form isocyanate like in previous case. So you can see here you are starting with the nitrine, and carbon migrates to the nitrogen and it form isocyanate. Finally, I've told you the mechanism of hydration of isocyanate is like this. You are adding water to this carbonate. This is electrophilic and this is nucleophilic, and this double bond break like this, and this carbon get OH, and this nitrogen get a lone pair here. That lone pair can abstract H plus from here and form carbonic acid. And usually this is the structure of carbonic acid, and it undergo a rearrangement to give ammonium salt like this, and finally it decarboxylate to give amine like you can show here, amine. So in Curtius also actual product is isocyanate. It is unstable to hydrolysis, and it hydrolyzes. Usually the isocyanate undergo attack by variety of nucleophiles such as water here, and alcohol it is here, and amine is here, to yield amine in the case of water and carbamate in the case of alcohol. If you are using alcohol for hydrolysis, it gives carbamate, and if you are using amine, you get urea derivative. Okay, that's about Curtius. And one example for Curtius is you can use for synthesis of alpha amino acid. For example, glycine can be prepared by Curtius reagent, and you are starting with a diester, and in the presence of base, one of its ester get partially hydrolyzed, and you can see that CO2 minus it become. Then it react with the hydrazine, and hydrazine react with this ethoxide will leave, and it can attack this. This is a nucleophilic center. This can attack this carbonate, and it leave and it form corresponding hydrazine. And finally, this one react with oxidize with HNO2 and it form azide. So Curtius reaction start material is this is the azide CON3. This on Curtius reagent, and here we are using HCl and ethanol, and you get you know this rearrangement carbonyl is usually removed, so you get CO2H and NH2. directly linked with this N and NH2, that's glycine. Right? Okay, third reaction is Schmidt reaction. This is named after Carl Friedrich Schmidt. And in this reaction, the difference is you are starting with carboxylic acid or a carbonyl derivative with react with azide. Usually this is best or effective with carboxylic acid, and under acidic condition it gives amine finally. Okay, so this is used for the conversion of ketone to amide also, that is shown here. Ketone you can convert into amide, and carboxylic acid also can be converted into amide by treating with azide, hydrozoic acid, HN3 in the presence of, this is important, the reagent is important, acid in the presence of acid. So we will see the mechanism of this reaction. First we are starting with carboxylic acid. Carboxylic acid in the presence of acid, what happens is if this oxygen lone pair get protonated, and this is a very good living group, hydronium, and it form acyl carbanium, acyl group, and this is very good electrophilic center, and hydrozoic acid react with this carbonyl group, and it form an intermediate like this. Okay, fine. This one it form an intermediate like this, and this is protonated isocyanate. This is, it form protonated isocyanate like this, and this nitrogen group detach or leave from here, and this one form a double bond, and this R migrate towards this nitrogen, and it form RNH plus CO. This is isocyanate itself, but it is protonated isocyanate. And in the presence of water, what happens is, okay, this water can attack this carbon, this nucleophile. Finally it get hydrolyzed, and it get hydrolyzed COOH. Then usually what happens in previous case, it form amine. Okay, and the last reaction is Lossen reaction. This is named after Wilhelm Lossen, and in this reaction orthoacylated hydroxamic acid, that is difference is RCONX, X is here RCOO group. Orthoacylated hydroxamic acid with base, it gives first isocyanate. In each case we are getting isocyanate, and finally isocyanate is hydrolyzed to give amine. And it differs from Hofmann rearrangement is that living group is carboxylate anion. This is carboxylate anion rather than bromide ion. So this starting material is ester of hydroxamic acid, and this is the one which is least useful method among four rearrangement. And coming to the mechanism of this reaction, we are starting the ester of hydroxamic acid. In the presence of base, it hydrogen get abstracted in corresponding carbanion forms, and this in every case what happens is R group migrate towards the nitrogen, electron deficient nitrogen, and this X minus leave here RCOO minus, and it form this carbanion can form a double bond like this. That is, it form a isocyanate, and finally hydrolysis of isocyanate take place. That mechanism we have already seen in previous case, and it form RNH2COOH, that is carbonic acid, and in the presence of base this hydrogen can be get abstracted, and finally it get decarboxylated to give amines. So this is amine, it forms amine. So in summary, we have seen four molecular rearrangement reaction. And what happens is in this rearrangement, carbon migration take place to the electron deficient nitrogen, and all four rearrangements are closely related rearrangement in which the carbon migrate from the carbon to the nitrogen. This we already seen. This is the skeletal movement that takes place in all this for molecular rearrangement. O minus get retain its pi bond, and R group migrate to the electron deficient nitrogen, and it form a isocyanate, and only the difference is the X, that is leaving group. In each case it is different, and if leaving group is bromine, it is Hofmann rearrangement, and leaving group is nitrogen, it is Curtius and Schmidt. And if the leaving group is this is OCOR, this ester, and this is Lossen rearrangement. Okay, that's all. Thank you for watching.